Dear students, this is a brief description on the last module, fifth module, mass transfer. So I am not elaborating things. I've already shared with you these class notes. So mass transfer can be of two types. We say that there are two modes of mass transfer. One is diffusion and another is convective mass transfer. So mass diffusion is transport of the particular component in a molecular level. Just like we have conduction heat transfer which happens in the molecular level. Sorry, diffusion, mass diffusion is also the transport of molecules or material in the molecular level. And what is the driving force for the transport of this mass diffusion? It is nothing but the concentration gradient of a particular component. And this happens in a stationary medium. So we will have a diffusion mass transfer only when the material does not have any bulk fluid flow. So in that way, we can say that mass diffusion is similar to heat conduction. So heat conduction is also known as heat diffusion. Now, how to calculate the diffusion mass transfer? Diffusion mass transfer is calculated using the law called Fick's law of diffusion. There are two laws for by the name Fick's law. So this one is in particular Fick's first law of diffusion, which can be given as n dot of the particular component A is equal to minus dAB into area into d by dx of Ca, where n dot A stands for the number of moles of the particular component which is diffused per second. Then dAB, d suffix AB is called the diffusion coefficient. So this is typically known as binary diffusion coefficient of the component A in a mixture of A and B. That is the meaning of this. So this coefficient is applicable for a mixture of two species A and B. And the species of our interest is a transport of species A. So we can say that this is just like say alpha or just like the conductivity K, etc. So minus dAB into A into dCA by dx, where A is the area of the passage through which the diffusion takes place, and C is for the concentration, molar concentration of the species A. So dCA by dx is a concentration gradient in the direction. So what is the unit of Na? Na will have the unit of moles or kilomoles per second. That's why to show it as a rate, I've put here a dot at the top. And this A stands for the component A. And the concentration, so this is a term which is not known. Ca is a concentration is represented here in how many moles per meter cube of the particular component. So this equation is in terms of the number of moles. So this equation can also be written in terms of number of, kilogram per second. Instead of moles per second, we can also write Fick's law of diffusion in terms of kilogram per second. Moles per second and kilogram per second ആയിട്ട് ചെയ്യാം. So if you multiply the left side as well as the right side of this equation by the molar mass of the particular component, this equation will become in terms of kilogram per second. So Fick's law can also be written on the mass basis. So somebody asked me whether it can be written like this or not. So the same equation can also be written in terms of mass. So if you multiply the previous equation with the molar mass of the component A, Then we will get m dot A is equal to minus dAB into area into d rho A by dx. So rho A is for the mass concentration. Mass concentration will have the unit of kilogram per meter cube. This is similar to our density, except that this pertains to the particular component alone in the mixture of A and B. So these are written side by side. N. Now, if we want to write the flux, then dividing that by the rate by the area, we will get the flux. So this is a mole flux, which is equal to minus dAB into dCA by dx, or which can also be written as mass flux, that is equal to minus dAB into d rho A by dx. Now, the relation connecting rho A, the mass concentration, and the mole concentration. So mass concentration is equal to molar mass into mole concentration. So in 3D this equation can be written just like a heat conduction equation. We can also have instead of conduction equation, we can have diffusion equation, mass diffusion equation. So in this case, we can write this as dou square Ca by dou x square plus dou square Ca by dou y square plus dou square Ca by dou z square. And a generation time, if it is there, is equal to 1 by d into dou Ca by dou t. The same, similar, all the relations are similar for heat conduction and mass diffusion. So here this n triple dot I've used if there is a generation, or if there is a source of a particular component being produced. So this can happen in cases where there is chemical reaction. In that case, a particular component can be generated within the volume uniformly. Now, this is the general things which we wanted to we discussed. Now there are two things like there are different scenario where diffusion can take place. We will just be familiarized with some two or three types of uh, cases. So such one case is called a equimolar or equimolal counter diffusion. So I'll try to explain that with the help of this schematic diagram shown here. So let's have two chambers A and B, chamber or chamber 1 and chamber 2, something like that. So chamber A and chamber B are connected by a tube of maybe preferably with a uniform cross section. Now initially chamber A contains the component A alone and chamber B contains the component B alone. They are at the same pressure and same temperature, and assume that they are not reacting each other also. So non-reacting, chemically non-reacting. So when we say that the pressure of component A and pressure of component B, species B, are the same at the same temperature, we can see that the number of moles of this gaseous component, suppose this is a gaseous component, number of moles of this gaseous component A and the number of moles of the gaseous component B are the same. So initially this will have a concentration, say Na, Ca, and the right side it will have the concentration of B will be Cb. These are to be equal. The number of moles of A and the number of moles of B in each of these initially are equal. Now, when we connect them each other, due to the concentration of the component A in the chamber B will be zero initially. So there establishes a concentration difference, and this causes the mass to diffuse from the component A to diffuse from chamber A to chamber B. Similarly, the component B will be diffusing from chamber B to chamber C. I mean, chamber A. So their concentrations are the same, concentration gradients are the same. So the rate at which the component rate of rate at which the component A diffuses from A to B will be same as the rate at which component B diffuses from B to A. But when we compare the mass diffusion, if we are taking the positive direction from left to right, from A to B, then one will be negative of the other one. Now we can see that when this diffusion is established, the rate at which the component A is diffused from A to B will be same as rate at which B diffuses from B to A, same in magnitude. So in that way, while this mass transport take place by diffusion, the pressure, the number of moles, the concentration, the pressure, etc., will be the same. Total number of moles will be the same throughout, or total pressure will be same throughout. So uh, this phenomenon is known as equimolar counter diffusion. Equimolar counter diffusion. So to find out the rate at which the components diffuse from A to B or B to A at any instant, an equation is derived, is formed. So this is the particular case we have equimolar counter diffusion. So we can say that just like we make the equations for heat conduction, we can make the equation for heat diffusion in this case. So if we write the mass flux N A divided by A, this suffix A stands for the component A and this A stands for the area A. Don't be confused with that. That is equal to minus DAB into DCA by the distance. So that we can write DAB into CA1 minus CA2. Just like we write T1 minus T2 by L. So CA1 minus CA2 by L. Where CA1 is the concentration at X equal to X1. CA2 is the concentration at X equal to X2. So we will have this L is the length of that passage in between. I'll show you the passage. So this length is L. Just like the way we have a conduction takes place through a particular material which is having a cross section length, etc. The same is applicable for diffusion as well. Similarly, we can write the the mole flux of component B, N dot B divided by area is equal to dBA into area. Sorry, this area should not be there. Sorry, this area should not be there because we have already divided this with the area. Into Cb1 minus Cb2 divided by L, where Cb1 is the concentration at the left side and Cb2 is the concentration of the species B at the right side. But in the case of equimolar counter diffusion, we can see that N dot A or N dot B divided by A is same in magnitude as that of N dot A divided by A, mass flux, or the total mass will be the same. I mean, mass flux or diffusion rate will be the same. So only thing is there is a negative sign because when we are taking Na from left to right, Nb is also taken from right to left. So from right to left, Nb will have a negative sign as that of species A. Now, there is some rearrangement to be done for on this equation. Since these are ideal gases, we can use the ideal gas relation uh, uh, to have this equation. So ideal gas relation, we can write to PV equal to nRT, nR bar T, where P is the partial pressure of the component A, V is the total volume of the chamber, and N is the number of moles of the component A, R bar is the universal gas constant, T is the absolute temperature. So in that way, uh, Now we can have from this relation number of moles per unit volume. This is uh, N divided by V. What is N divided by V? Number of moles of the component divided by volume will be the uh, molar concentration, nothing but molar concentration N by V. N dot and N are different. So N by V is equal to P divided by R bar T. P divided by R bar T. And this is nothing but the concentration Ca. Moles per or kilomoles per meter cube. So Ca can be replaced with the Pa divided by R bar T, where Pa is the partial pressure of the component or the species A, which is our interest. So this relation can be written as N bar divided by A is equal to DAB. Ca can be written as Ca1 can be written as P1 divided by RT, and Ca2 can be written as P2, Pa2 divided by RT, and L will be in the denominator. So in total we have N dot A divided is by A is equal to D by R bar T into Pa1 minus Pa2 by L. So you don't even so if you compare everything with the conduction equation, we can easily make and learn these things by heart. So DAB is a coefficient, mass diffusion coefficient, and for conduction equation, that is conductivity is taken there. So let's just see an example. Carbon dioxide and air experience equimolar counter diffusion in a circular tube whose length and diameters are 1 meter and 50 millimeter. The system is at a total pressure of 1 atmospheric atmosphere and at a temperature of 25 degrees Celsius. The ends of the tubes are connected to a large chambers in which the species concentrations are maintained at fixed values. The partial pressure of carbon dioxide at one end is 190 millimeter mercury, and the partial pressure of carbon dioxide at the other end is 95 millimeters of mercury. Remember, 760 millimeters of mercury is 1 atmospheric pressure. Estimate the mass transfer rate of carbon dioxide and air through the tube. And the mass diffusion coefficient of carbon dioxide in a mixture of carbon dioxide air is given to be 0.16 into 10 raised to minus 4 m square meter square per second. So this diffusion coefficient will have the same unit as that of uh, thermal diffusivity or kinematic viscosity. These are similar terms but with different physics. So the equimolar counter diffusion equation will be N dot of our component A here is the carbon dioxide, which is equal to D divided by R bar T into area into P1 minus P2 of carbon dioxide divided by the distance between them. Now we need to substitute each and every equation so that we can get this. So diffusion coefficient value is given. R bar is 8314 joule per kilomole per Kelvin. T is the temperature in Kelvin. Then PCO2 1 and PCO2 are converted into proper SI. So 190 millimeters of mercury will be 190 by 760 into 101325 Pascal. Then P2 of the species carbon dioxide is 95 millimeters of mercury. That's converted like this. 95 by 760 into 101325. So this will be 0.25 into 101325, and this will be 0.125 into 101325 Pascal. So we need to write them in terms of Pascal, proper SI. Now area is pi by 4 d square, that is pi by 4 into 0.05 square, etc. Substituting these values, we will get n dot is equal to, we substituted everything properly, so then this will become 160.6 into 10 raised to minus 12 kilomole per second. Now if you want to write this in terms of kilograms, This is to be multiplied with the area, I mean the molar mass of carbon dioxide. Carbon dioxide is a species of our interest. So its molar mass is 44. So mass diffusion rate of mass diffusion of carbon dioxide in the binary diffusion is equal to mCO2 into n dot CO2, that 44 into 160.6 into 10 raised to minus 4 kilogram per second. Now, interestingly, in equimolar counter diffusion, n dot of CO2 should be same as n dot of oxygen. So there are two components. Component A is carbon dioxide and component B is air. Carbon dioxide and air forms the mixture. So in equimolar counter diffusion, n dot of carbon dioxide is equal to negative of n dot of air. So since n dot of carbon dioxide equal to this much, n dot of air will be negative of this. So only the mass rate of, sorry, only the mole flux or mole rate will be the same. Mass rate will not be the same. Mass rate can be obtained by multiplying the mole flux or mole diffusion molar rate with the molar mass. So now I think the confusion with the molar rate and mass rate are clear. We can use the Fick's law of diffusion in terms of mass or in terms of uh, moles. But remember that in equimolar counter diffusion, only the mole rate will be the same in magnitude but opposite in direction. So again for air also we can calculate n dot air is equal to negative of n dot CO2. That is why opposite direction. So m dot air is equal to molar mass of air into n dot of air. Molar mass of air is different. 28.84 into the same thing. So the final answer is written in terms of per hour basis. So minus 1.667 into 10 raised to minus 5 kilogram per hour. So equimolar counter diffusion occurs in the case of two gases which are allowed to mix together provided the initial concentrations are the same only, or initial pressure and temperature of both the components in the mixture are the same and they are allowed to diffuse over a passage having a length and a diameter or length and a cross section, etc. This is a case of equimolar counter diffusion. Now there is another type of diffusion in which say uh, a particular component will be diffused into another component which is stationary. Uh, the other component will not be diffused back into this one. Let's assume the case where we have water taken at the bottom of a test tube. A test tube having say 10 centimeter length or height and some diameter, and we have water collected at the bottom. So here uh, uh, we can just think of the case when water evaporates into the dry air. So we have stationary air which is at the top of this, which is everywhere, which is not flowing, stationary air. Now, if here we have water, the water molecules will be evaporated into or diffused into the air, and the concentration of water molecules in air will be corresponding to the saturation pressure at that temperature. Suppose we have temperature 30 degrees Celsius. We can get from the steam table that corresponding to 30 degrees Celsius, what will be the saturation pressure of this water in air. So total atmospheric pressure will be sum of the partial pressure due to water vapor and partial pressure due to dry air component. And partial pressure due to water vapor can be maximum if it is fully saturated. So here we assume that just above this liquid water level, the pressure is a saturation pressure corresponding to that temperature of water. So diffusion of water is our interest. Now in this case, it has been derived that the rate at which water is evaporated into dry air or into an air which is stationary over this height will be given by DAB into total pressure divided by R bar T into distance into log of P minus PA2 divided by P minus PA1. This equation, all these equations are there in the data book. Just if you get some problem, you need not even learn this by heart. Even it's easy to learn, but you need not learn this by heart. You can just refer to the particular case, whether it is an equimolar counter diffusion or it is a stationary evaporation of water, etc. So evaporation of water is an example of diffusion of a component into a stationary medium. So here two species are, the species of our interest is water evaporate into vapor. I mean evaporate into atmospheric air. So water is our component of interest. Here understand that water vapor or water molecules are very minority in this component. So this minority component is our interest. We want to calculate the rate at which water is evaporated into dry air without any wind or without any air movement. So here this is the total atmospheric pressure. This is the binary diffusion coefficient of water in a mixture of water vapor and air, and this is the rate at which water is evaporated into or diffused into dry air given by number of moles of water per meter square. So this is flux. And R bar 8314, T is the temperature in Kelvin and L is the distance. So here we have water at this, and the concentration of water here can be found out if we know the saturation pressure corresponding to that temperature. And here uh, above this column we have air. Air can be dry air or air. This air can also contain some water vapor in it, but its concentration will be less than the concentration of water vapor at this. So that diffusion will be there. It is pure evaporation of water vapor without any wind over that. So this equation is there. Now P is the total pressure and PA2, PA is the partial pressure of water vapor. This A stands for the particular component of our interest. So our component, interest component is water vapor. So PA at this height and P minus PA1 at this height. So if we can calculate partial pressure of water vapor at this level and partial pressure of water vapor at this level, then we can substitute this. So you remember P is the total pressure, total atmospheric pressure. Total atmospheric pressure is sum of partial pressure due to water vapor and partial pressure due to dry air component. So even this equation you can get from the data book, and if problem is asked, you can do this problem. Now there is a example from this topic. So estimate the diffusion rate of water at 27 degrees Celsius from the bottom of a test tube which is 20 millimeter in diameter and 4 centimeter long into dry air at 27 degrees Celsius. Given the diffusion coefficient of water in air is equal to 0.26 into 10 raised to minus 4 meters square per second. So our equation is n dot AX is equal to DAB into total pressure into A divided by R bar T into X2 minus X1. This is L length into ln P minus PA2 divided by P minus PA1. Substituting the values, now we need to calculate partial pressure PA2 and PA1. So remember, go back to the figure, we can see that this is the partial pressure at this point is PA1 and partial pressure at this point is PA2. and the diffusion takes place from this side to bottom to top. uh, because here we have water collected here. Just immediately above this level of water, the air will be saturated. That assumption we take. So from that assumption, now how to get that? So concentration can be obtained, or the pressure can be obtained. PA1 is equal to saturation pressure corresponding to 27 degrees Celsius, which can be obtained from the steam table. Your HMT data book will also have this property in it. So you can refer to the data book and get the saturation pressure of water vapor corresponding to 27 degrees Celsius. That will be PA1. Then PA2, we can assume that it is dry air. Equimolar counter diffusion takes place into dry air. So I'll show you this question. See, 4 centimeter long into dry air. So dry air will have only dry air component and there will be no water vapor component in it. So that it will be zero. You can say that it will be zero. So substituting the values, uh, we can get this into substituting all these, and also if you want to get the answer in kilograms of water per second which is evaporated, that should be this equation should be multiplied with the molar mass of water, which is 18. So substituting everything, 18 into diffusion coefficient 2.26 into 10⁻⁴ meters per second into total pressure is 101325 pascal into area pi by 4 into 0.02 square into log P minus 0. P is the total pressure because it is dry air at the top, and P minus PA1 101325 minus the saturation pressure is equal to 0.03531 bar from the tables. So this will be equal to 3531 Pascal. That is substituted here, log or something. So finally, we will get 5.3 into 10 raised to minus 9 kilogram per second. Or we can say multiplying by 1000 and multiplying by 3600, we will get gram per hour. This many gram per hour, water will be evaporated into the dry air, stationary dry air. So that is the second. So uh, that was the examples which we can expect for the examination based on diffusion, mass transfer. Now we have convective mass transfer. Just like we have conduction heat transfer and a convection heat transfer, there will be mass diffusion and a convective mass transfer. Convective mass transfer occurs when a fluid uh, flows over the surface of species A. Suppose we have a particular species A, like water in a pool, and wind blows over the water. So wind is basically air. uh, then evaporation of water will be faster actually because there is convection mass transfer takes place. Just like a wet cloth will be dried fast when there is wind over the cloth. So this is actually the example of convective mass transfer. Convective mass transfer equations are similar to those of uh, heat transfer, convection heat transfer. The region, even suppose we have a species here and some fluid flows over this. So the fluid which is flowing will have a mixture of A and B, and the surface will have the component A here. So the concentration just near to the surface of component A will be high, and the concentration of the species A in the flowing fluid will be less. So we have free stream condition. So free stream concentration of the species A in the uh, gas which is flowing or liquid which is flowing. So there is a region where majority of the concentration difference takes place from the surface concentration to the free stream concentration, just like we had a thermal boundary layer. So this small region of which 99% of the concentration variation of the species A takes place is called the species concentration boundary layer. Species concentration boundary layer. So here we have the flow direction x direction and free stream velocity u infinity of the gas or liquid, which is a mixture of A and B. And our interest is how much A diffuses into the free stream. So the convective mass transfer NA, N dot A, can be written as just like we have convection heat transfer H into area into C concentration of species A at the surface minus concentration of species A at the free stream. So here this coefficient similar to convective heat transfer coefficient. This is called the mass transfer, convection mass transfer coefficient, convective mass transfer coefficient. So we can get the unit of convective mass transfer coefficient by say Na divided by A into Ca minus Ca, Cas minus Ca infinity. Substituting the units of all, we can see that convective mass transfer coefficient will have a unit of meter per second. We can see that the unit of convective mass transfer is meter per second. So this is just like Newton's law of cooling. So this is for convective mass transfer, a similar equation. Everything is similar. The coefficient is written with a subscript m to show that this is convective mass transfer. And H without m is actually convective heat transfer coefficient. A is the surface area from which the convection of the mass takes place. Ca is the concentration in kilomole per meter cube of the species A at the surface. And Ca infinity is the concentration of the species A at the free stream. Again, kilomole per meter cube. Now we can have the boundary layer equations. Suppose we have mass transfer also there in a flow field. We can write the continuity equation inside the boundary layer, the momentum equation, only x momentum will be there, the energy equation and the species equation. Species equation can be written in the same way. U into dou Ca by dou x plus V into dou Ca by dou y is equal to dAB into dou square Ca by dou y square. And not elaborating much onto that. Now we have correlations to use to find out the convective mass transfer. In a convection heat transfer, the primary aim is to calculate the value of heat transfer coefficient. Just like that, in mass transfer, convection mass transfer, the primary aim is to calculate the convective mass transfer coefficient, which can be obtained just like an equation which we used for the convection heat transfer. So before using those equations, we should know the different parameters. We've already studied. Uh, so Nusselt number is actually HL by K or HX by K. Nusselt number is HX by K. Similarly, in convective mass transfer, instead of Nusselt number, we have something called the Sherwood number represented by SH. So in convection heat transfer, we have Nusselt number. In convection mass transfer, we have Sherwood, which is given by Hx by d, H mass x by d, where d is the diffusion coefficient, binary diffusion coefficient. Now, Prandtl number is defined as nu by alpha. Schmidt number is again. So now we have three diffusion coefficients. One is the molecular momentum diffusivity called, kinematic viscosity nu, then the thermal diffusivity alpha, and we have the binary diffusion coefficient D. All will have meter square per second as a unit. Now, Schmidt number is defined as Schmidt is having the spelling of SCHMIDT, Schmidt number with the SC. Sherwood is SH, which is analogous to Nusselt number. So Schmidt number is equal to nu by D. And we have a relation connecting alpha and D. So alpha by D is known as Lewis number. Lewis number represented by Le is equal to alpha by D. So these may be asked for the examination, or for gate and other things this will be asked. So interestingly, we can see that Lewis into Prandtl equal to Schmidt. You should remember this for future also. So now we have correlations. We have correlations to find out the Nusselt number. Uh, just like that in convection mass transfer, we have correlation to find out the Sherwood number. From the Sherwood number, we can obtain the convective mass transfer coefficient HM. So Sherwood number is basically a function of Reynolds and Schmidt number. We know that Nusselt number was a function of Reynolds and Prandtl. Sherwood will be a function of Reynolds and Schmidt number. So typically, for example, all of us, we had seen that for laminar flow over a flat plate, laminar flow, even though I did not write, for laminar flow over a flat plate, Nusselt number is given by 0.332. Local value of Nusselt number equal to 0.332, Re to the power of 0.5 into Pr to the power of 1 by 3. Similarly, similar case, a Sherwood number can be calculated as the similar equation 0.332 into Reynolds to the power of 0.5 into, instead of Prandtl, we should have Schmidt number to the power of 0.33. So this is one example. Almost all the equations, Nusselt number equations, we can have corresponding Sherwood number equations also. This is analogous. We can make the analogy between momentum transfer, heat transfer, and mass transfer. So now just see the analogy. You are familiar with the uh, uh, this relation. Cf by 2 is equal to Nu by Repr. This analogy is known as Reynolds analogy. Reynolds analogy is applicable for fluids having Prandtl number Pr equal to 1, almost equal to 1. Then we can write Cf by 2 is equal to Nu by Re or Repr. Pr can be 1. This can be extended to this relation also. Sherwood divided by RESC. So this is actually applicable for fluids with the Prandtl number equal to Sherwood number equal to 1. If Prandtl and Prandtl number equal to Schmidt number equal to 1. Prandtl and Schmidt are 1, then Lewis will also be 1. But Lewis we are not considering it for the time being. You already know that Nu by Repr is known as standard number, STANTON, standard number. Nu by Repr equal to standard number. Similarly, Sherwood divided by RESC is known as mass transfer standard number. Mass transfer standard number. SC divided by SH divided by RESC. So all are analogous. Hence we have the analogy. Now Reynolds analogy is applicable for fluids with the Re equal to 1 and PR equal to 1 and Schmidt equal to 1. Now for common any fluid combinations, we can have a better analogy called Colburn analogy or Colburn-Shilton analogy, etc., or modified Reynolds analogy, sometimes known as like that also. So this will be Cf by 2 is equal to Nu by Repr to the power of Prandtl raised to 2 by 3, which is also equal to SH divided by RESC to the power of into Schmidt to the power of 2 by 3. All these will be given in the data book. You know this because if you answered about these questions. So this is more powerful equation Reynolds-Chilton because this can be applied for any fluid. Uh, One thing we should remember is that uh, this analogy can be used to calculate. For example, the heat transfer coefficient can be calculated for a particular fluid whose Prandtl number is known uh, if you know the friction coefficient. Even without knowing the temperatures and things like that, if the coefficient of friction is given for a fluid with this particular Prandtl number, then heat transfer coefficient can be calculated. So that is a power of use of Kolbe analogy. Similarly, on this side also it can be like mass transfer can be calculated, or convective mass transfer coefficient HM can be calculated if you know the coefficient of friction of that fluid. So these are the things which I wanted to share with you. There can be a problem from this topic also. For that, you have to use the analogy, any of this analogy along with the particular equations. So it is too late for me to share these things with you, but those who are interested can read the notes, which very brief note. I did not write the essential things even, just to go through, and which might be helpful for you for tomorrow's examination. Bye. Thank you, one and all.